Hi, everybody. This is Miss Eisencraft with Unit 3, Lesson 5, Practice Problems. So let's go ahead and get started. So we assigned numbers 4, 5, and 6 only. All right. A seed is planted in a glass pot. Okay, that's important, because how else would you be able to see where the seed was when it was under? And its height is measured in centimeters every day. The best fit line, which is this blue line here that they either got from technology or just by eyeballing it, is given by this equation. Holy decimals, right? Where y is representing the height of the plant. So this is the height in centimeters, cm. And this right here is an x is representing the number of days since it's been planted. Okay. All right. What is the slope of the best fit line? So we don't have to calculate the slope here by doing change in y, change in x, or any slope triangle because it was already found for us. If an equation is in this format, right? This right here is known as the slope. Okay, so we are literally going to take 0.404, leave off the x. Now, if you put it over 1, it's really easy to interpret it. Slope is known as the change in y over the change in x. So this is how many centimeters, and it's positive, it is increasing every day. So, a little bit less than a half a centimeter a day. You can also sometimes hear it said, well, for every 1 day, it's increasing 0.404 centimeters. You can flip it around, but I often like to read it like the ratio or the rate. This is how many centimeters per day. I like to read it as the change in y over the change in x. But for every day, it is going up about 0.404 centimeters. And that's approximate because it looks like some days it's not growing as fast. Okay, but the interpretation is it grows approximately 0.404 centimeters each day, or for every day, it grows that much. All right. What is the y-intercept of the line? Okay, the y-intercept. Visually, y-axis, where does it cross? Okay. And in the equation, it is always this part. Take the sign with it, right? Since the equation is negative just kidding, 0.404x, that was the slope. We need to take the sign with it. That is the y-intercept. Hey, and it looks like where it is there. You can also think, okay, on day 0, what was the height? How was it negative? Hey, because it was planted under the dirt, right? In the dirt. So it is reasonable that on day 0, the height of the seed is negative 5.18 centimeters if you consider like the level of the dirt 0. So 5 centimeters under the dirt. On day 0, the seed is planted approximately 5 centimeters under the dirt or whatever. All right, and that does make sense. All right, let's keep going. Number 5. At a restaurant, the total bill and the percentage of the bill left as a tip is represented in the scatter plot. All right, so they call this the best fit line, or you might hear it called the line of best fit. Same thing, as represented by this equation. Again, don't get super freaked out about all the decimals, but let's label things. X is the total bill. So how much was the total bill? And then this is measured in dollars. Yeah, that's how we pay for things. And then Y is representing the percentage of the bill that you left as a tip. This is the percent. I guess the best way to generally explain this is oftentimes when you have like a coffee drink, say it's $5, you might leave a $2 tip, which is a huge percentage of what you paid for it. When a meal gets more expensive, you might be a little bit more conservative in the percentage you give to the tip, because it's going to be more money. So that's what the scatter plot is showing. It's not a very strong or a great line of best fit because the dots are kind of everywhere, but they do say are showing a trend that it's going down. As the total bill is increasing, the percentage people are tending to leave is going down. There's a couple dots pretty far away from the line. Okay. So what does the best fit line estimate for the percentage of the bill left as a tip when the total bill is 15? I'm adding. So when your bill is $15, what are they saying is reasonable? I like to first look at it. If there's a line, try $15, go up and see where it is. And then we'll use the equation. Right? This point here looks like a $15 bill, like a total $15 bill for a meal. The line of best fit is showing that somebody would leave like an 18% tip. Okay, let's see if the equation actually gives that. So this is your X, and it's asking you to figure out the Y is the percentage. So let's use the equation and let's put 15 in place of X, and then just do a little bit of math. You can use Desmos calculator or anything. Remember, that's negative. Do not expect you to do that by hand. Negative 0.63, oh my gosh, 632 times 15 plus 27.1. Hey, so this is, again, you're finding the percentage of bill left as tip. That's what the line of best fit is saying is a good approximation, and it looks like that 18% is what we kind of eyeballed on our line, and it's very close. Hey, now it's important to, this is like, if you're interpreting this, it's saying it's going down, right? The percentage is going down like over a half point. I just like to look at this part, a little bit more than a 0.5%. Every time the bill goes up by $1, and it has a y-intercept of 27.1, which is kind of a weird intercept here. But the linear model, is helpful in making sense of like this little range, but it might not make sense as you go further out. Let's look. So what if you spend, well, this linear model makes sense for somebody who spent $50. Well, we can't see it on our graph at all. You can even imagine, it looks like $50 is going to go down here. So is that going to make any sense? Let's try it. For $50. Okay, what would that be? I'm going to hit second enter, and I'm going to go change that to 50. Little pro tip. You would leave a negative tip? I mean, I don't think so. It's like taking money from them. So that would kind of indicate that linear models, they're good in making sense of data, but maybe just in this range, like from items that are costing you, like at a cafe or something, like $0 to $30. But much beyond that, this linear model doesn't make much sense. So for the $50 bill, this linear model wouldn't make any sense. Maybe it levels off at this point, right? Like at a certain amount. But it's just important to know the linear models are kind of made up to make sense of a trend. And then after a certain point, the dots might be doing something different. And when we keep projecting out to more and more expensive meal, this isn't making sense. So no, a negative percentage doesn't make sense. Doesn't mean the linear model is wrong. It just means it's limited in its use. Okay. All right, last one. I think this one's a fast one. Yay. Lots of words, but a recent study investigated the amount of battery life remaining in alkaline batteries of different ages. The scatter plot shows this relationship between the different alkaline batteries tested. Okay, so it looks like we have to kind of figure this out here, but this is years. I'm going to look in your book real quick. Does it say that, or do we have to figure that out? Because on this graph, it is not showing years. Yeah. So here, I'm sorry, the PDF doesn't have it, but your book has it labeled. So this is the age of the battery. Like how many age of the battery? Give your battery a birthday party. Oh my gosh. Okay, years. And then over here, this is their battery life in hours. Okay. So it's just asking you, this was already labeled. You could probably have like figured out what that meant. It told you the titles up here, but it was already labeled in the book. It just left it off the PDF for some reason. I'm sorry. So this right here, 715, it's asking you to interpret that. The easiest way to do it is to remember this is X and this is Y and to put the labels there. Okay. A 7-year-old battery has, like 15 hours of life. Okay. A 7-year-old battery has about 15 hours of life left. There we go. All right. Super simple. All right. See you later.